Let's look at a surface of revolution. In the earlier part of the course, we actually wrote the surface of revolution in terms of Cartesian coordinates. So to remind you of that, let's look at an example. Say we have x equal to sine z, where z runs from 0 to pi. And what we want to do is rotate this curve about the z-axis. Then that's going to actually form a circle in a plane parallel to the xy plane. So we get x squared plus y squared equals sine z squared, where of course sine z is the radius function. And this would give you the equation that we had earlier. And of course now this reminds us of equations of ellipsoids, spheres, hyperboloids. All of those types of surfaces are surfaces of revolution. But now what we want to do is write this parametrically. So I'll use the same technique that I used in the previous problem. Let's go ahead and divide by sine z, where of course it's non-zero. So we get x divided by sine z squared plus y divided by sine z squared equals 1. So again, this looks like the conic section technique we used in the previous problem. And now using the coordinates u and v, we're going to set the z equal to v, which runs from 0 to pi. And now, of course, what we want to do is to abide by this 1 here. So we want to absorb the sine v, so we need a copy of that in each of the x and y. And then we want to, again, compensate for the 1 that we have here. We can use a cosine u and a sine u upon squaring, giving us the fundamental identity. So what we have now is x equal cosine u sine v and y equals sine u sine v, where u runs from 0 to 2 pi. And then, of course, that will give us a parametric representation. This by no means is unique. However, it is easy to do. So now our parametric representation of this surface of revolution will be x coordinate cosine u sine v, y coordinate sine u sine v, and z coordinate v, again, where v runs from 0 to pi and u runs from 0 to 2 pi. And we are done.